Okay. So, what we have seen so far is that if you had a function that was periodic with period 2L, okay, you could express it as a Fourier series. Okay, you could write it as a linear combinations of cosines, sines and a constant term. Okay, and we saw the expressions for each of the a n's and each of the b n's. Okay, and so this Fourier series is one of the pillars of modern computational science. Okay. So in almost all fields of engineering and science, you will come across a Fourier series. If you have arbitrary functions, you expand them in terms of these Fourier series. Okay. Now sometimes we use the exponential form of Fourier series. Okay. So, in this you write f of x is equal to sum over n equal to 0 to infinity or n equal to minus infinity to plus infinity C n e to the I n y x over L. Okay. Okay, so, n equal to minus infinity to plus infinity C n times e to the I n pi x by L. Okay. So, this is the exponential form of the Fourier series, and this does one thing. So, it helps to extend it to complex functions, and in some cases it turns out to be easier to work with this. Okay. Now, this series is identical to this series. Okay. If you notice that C n is equal to a n minus I b n by 2, okay, and C of minus n, okay, so this goes from minus infinity to plus infinity. Okay. So, C of minus n, okay, this is equal to a n plus I b n by 2. Okay. So, so you can show this quite easily. I mean, by just doing this expansion, taking the terms separately. So, C 0. Okay. So, you will find that C 0 is equal to a 0 by 2. Okay, because n equal to 0. So, C 0 is a 0 minus b 0 is 0. So, a 0 by 2. Okay. And then each for C 1 you will have C 1 e to the I pi x by L. Then you will have C minus 1 e to the minus I pi x by L. So, so when you combine those two, you will get something that relates to A1. So, by inverting the relation, you can show that C n is this and C minus n is this. Okay. So, this is the exponential form of the Fourier series, and this is also something that is commonly used. Okay. Now, in this form of the series, we said that we can extend it to complex functions. Now, suppose f of x is a real function, okay. So, if f of x is a real function, you can show that C n is equal to C minus n star. Okay. So, this is something that you can show quite easily. Okay. To show this, what you want to say is that you have C n times e to the I n pi x by L, and you have C minus n e to the minus I n pi x by L. Okay. So, you rewrite that as C n plus. To show this, you have C n e to the I n pi x by L plus C minus n e to the minus I n pi x by L. So, you will have two terms in this series that will appear in this form, and they should add up to give something that is real for all values of whatever choice of, and we want to find the appropriate choice of C's that give that. So, I can write this as C minus n x by L by L. Okay, so you will have one term that looks like this, and you can write the other term as okay. So, so what I did was I added a C n e to the I C or C minus n e to the I n pi x by L, C n e to the minus I n pi x by L, and I should subtract those terms, okay, and a factor of 2. So, if you add up these two, you will get there should be a factor of 2. Okay. So, and this whole thing has to be real. Okay. And what that will imply is that these combinations have to be real numbers. Okay. And one way to get that is if the imaginary parts of C. So, what we will say is that if f of x is a real function, then C n, it turns out, will have to be equal to C minus n star. Okay. And you can see this fairly easily, because each of the terms here has to be a real number, and this has to be true for all n. Okay, this has to be true for all n, and C0, in addition, C0 has to be real. Okay. So, this is the condition. So, if f of x is a real function, then C n has to be equal to C minus n, the complex conjugate of C minus n. So that what you have is a number plus its complex conjugate, which has to be a real number. Okay. So, if that is true, then you have C n by L, and you have sum over n equal to 1 to infinity plus C 0. Okay. So, so this series I write in this form, okay, and and this is equal to f of x. So, if f of x is real, we say that this has to be real, okay, and then if C n equal to C n star, okay. So, if this is C n star, then this is then this that implies this is C n e to the I n pi x by L star plus C n e to the I n pi x by L to infinity plus C 0. So, this is real. Now, this is, notice that what appears here is exactly this. Okay. So, a number plus its complex conjugate, this whole thing has to be a real number, real. Okay. So, if you have a complex number like a plus I b, the complex conjugate of that is a minus I b, and so this is real number. So, it is just 2a. Okay. So, so if you have a real function, then the Fourier series becomes it in the exponential form has this condition between C n and C minus n. Okay. Now, next what we will do is we will try to take different limits. So, here we chose a boundary condition where the function was periodic between minus L and L. Now this L can be anything, okay, and very commonly we take L equal to 2 pi, L equal to pi. So, 2 L is 2 pi, okay, and this is also very popular in lot of applications. So, let's write the series when L equal to pi. So, if L equal to pi, you can show that your Fourier series becomes cos. Now, you have n pi x divided by pi. So, that is just n x plus b n sin n x. Okay. And in this case, f of x plus 2 pi is equal to f of x. Okay. And this is also a very common form of Fourier series that is seen in various applications. Okay. Now, there are a lot of interesting expansions for sines. You have the Taylor expansion for sine as an infinite series involving pi. Okay. Now, there are also a lot of interesting inverse relations for where pi can be written as a sum of sine functions. Okay. And you can often see this when you do Fourier series. Okay. So, one example is you can show that sum over n equal to 1 to infinity 1 over n sin n x. Okay. So, if somebody asks you what is the value of this, series. So, this is equal to, so when n equal to 1 this is sin x, when n equal to 2 is sin 2 x by 2, when n equal to 3 it is sin 3 x by 3 plus so on. Okay. And suppose somebody asks you what is the value of this series, then it is not very obvious by looking at the series, but what you can do this quite easily when you see the Fourier representation. So, what you will say is that a n, so you say let f of x is equal to sum over n equal to 1 to infinity 1 over n sin n x. Okay. So, we just say let f of x is this. Now, what we will do is we will write f of x as a Fourier series. So, a 0 by 2 plus sum over n equal to 1 to infinity a n cos n x plus b n sin n x. Okay. Now, since sin n x is a periodic function, I just with period 2 pi, I just wrote it as a periodic function in period 2 pi. Now, this implies a n equal to 0, a 0 equal to 0 and b n equal to 1 by n for n not equal to 0. Okay. So, for all n not equal to 0, b n is equal to 1 by n. So, now what you want is the following, you want 1 by n is equal to integral from integral 1 over pi from I can do from minus pi to pi, okay, from minus pi to pi, and what I will get is sin n x f of x dx. Okay. So, what you need to have is that the value of this integral should just be 1 over n, or value of this integral should be 1 over n, and also you should have 1 over pi integral minus pi to pi cosine n pi x by L n x cosine n x f of x dx. Okay. And also the integral under f of x. So, when n equal to 0, so also 0 equal to 1 over pi integral minus pi to pi f of x dx. Okay. So, you want a function that is, first of all, the function has to be an odd function. So, implies f of x is odd. Okay. If it is an odd function, then automatically then cosine of not only will this be true, but also cosine of n x f of x will be true for all positive n. Okay. It has to be odd. Now, if it is an odd function, then then since sine is also an odd function, f of x is also an odd function, I can write 1 over n is equal to 1 over pi integral 0 to pi. So, I can write 2 over pi integral 0 to pi sin n x f of x dx. Okay. All right. So, now you might say that okay, you still do not have the value of f of x, but you can get the value of f of x quite easily just by inspection. You know that suppose you had f of x was a constant. Okay, so suppose f of x was a constant, then integral sin n x from 0 to pi will give me 1 over n sin n x. Okay, it will just give me 1 over n sin n x. Okay, so so then what I am going to demand is that f of x since it has to be odd. Okay, so if for positive x this was just a constant or just a simple function of x, then you would get if it was a constant, then you would get a 1 by n, but a constant turns out to be an even function. So what we will say is that let f of x is equal to a plus bx. Okay, so if we will just let f of x equal to a plus bx, now you can immediately see that 1 over n f of x, this is for 0 less than equal to x less than pi. Okay, so then 1 over n is equal to 2 over pi. Okay, now the first term will just give me sin n x divided by n from 0 to pi times a plus the plus b times integral x sin n x from 0 to pi dx. Okay. Okay. Now, this term goes to 0. So, this term goes to 0. So, so this just becomes over pi 0 plus. Now, what we have is b times this integral x sin n x, and you can integrate this by parts. The first term will be x times cos n x by n between 0 and pi, and the second term is minus integral cos n x by n from 0 to pi dx. Okay, and this whole thing multiplies b. Okay, so then you can show this. I'll take the pi by 2n is equal pi by 2n, and I'll bring the b down, pi by 2n b. Now, this is when x equal to pi, you get cos n pi by n. Okay, so cos n pi by n. So you get pi times cos of n pi by n, and cos n pi is minus 1 raised to n by n. Okay, so cos n pi by n, and in this case your integral of cos n x will give me sin n x. Okay, sin n x from 0 to pi will just give me 0. Okay, so so what you see immediately is that this is equal to so this implies b is equal to 1 by 2 minus 1 raised to n. Okay, so b is just 1 by 2 minus 1 raised to n. Okay, now then what about a? How do you choose the value of a? Now you have to choose a such that you get an odd function, okay. And so what we will do is the following. We will choose a. So a0 is pi. Okay, let us just choose a0 equal to pi. Okay, I will motivate this in very shortly, but what you will finally get is the following, that f of x is equal to half pi minus x. Okay, this is for 0 less than equal to x less than equal to pi, and f of x equal to half pi plus x for minus pi less than equal to x less than equal to 0. Okay. So, what you will get is that f of x satisfies this sort of relation, and so what we finally got out of all this is that this function has a Fourier series that just looks like 1 by n sin n x. Okay. So, this function is also is the same as a sawtooth function. So, if you plot this, okay, so when x is greater than 0, this looks like pi minus x. When x is less than 0, it looks like pi plus x. So, that will look like this. Okay, sorry, this should be minus. Okay, so this is minus pi, this is plus pi. And what you have is f of x is an odd function. Okay, it is an odd function, and the Fourier representation is just 1 over n sin n x. Okay, and you can easily verify that that this satisfies this sort of expression. Okay. Now, what is remarkable is the following. There are two things that are remarkable. One is that your function looks very discontinuous. Your function has this sharp discontinuity, but if you look at the Fourier representation, it looks perfectly continuous. So essentially this is this discontinuous function. Okay, a function that looks very discontinuous is represented by this nice looking Fourier series. Okay. So Fourier series, one of the things that is an important application of Fourier series is to convert functions that are very discontinuous into a sum of continuous functions. Okay. Now, the next thing is, suppose I take this and I put x equal to pi by 2. So if I put x equal to pi by 2, then what I get is x is greater than 0. So f of pi by 2 is just half pi minus pi by 2, that is pi by 4. Okay. Now, on this side, what I get is the following: if x is pi by 2, sin n pi by 2, okay, sin n pi by 2 is equal to 1 if n is odd, and it is 0 if n is even. Okay. So what you find is the following. You can write, so pi by 4 is equal to, now I will write this sum explicitly to make things clear. So when n equal to 1, so you get 1 into pi by 2, that is sin pi by 2, that is 1. So this becomes 1. Okay. Now when n equal to 2, this becomes sin 2n pi by 2, that is sin pi, and sin pi is 0, so you get 0. N is 3, this is sin 3 pi by 2, that is minus 1, so you get minus 1 by 3. Similarly, you can show plus 1 by 5, minus 1 by 7, plus 1 by 9, and so on. So this is another representation for pi. Okay. So pi can be expressed as this infinite series. Okay. Or pi by 4 can be expressed as this series. So, in this way you can derive lot of series for pi using this method of Fourier transforms. Okay. So, the last part I want to do in this lecture on Fourier transforms on Fourier series is to give the orthogonality relations. In this case the orthogonality relations will, instead of minus L to L, you will have minus pi to pi. Okay. So, that is the only change. I will write those on this side just to complete our discussion. Okay. So, I can write this as integral. Now, I can choose my limits as minus pi to pi, or I can also choose it from 0 to 2 pi. There is no difference. Okay. So, the orthogonality relations are cos mx sin nx is equal to 0, and then you have integral 0 to 2 pi 1 over pi, sorry. This is equal to integral sin mx nx equal to mn. Okay. So, so because of the periodicity, I can shift my interval to 0 to 2 pi without any change, and I can write my, so this is equal to 1 if m is not equal to n, and equal to 0 if m is 0 if m is not equal to n, and 1 if m is equal to n. Okay. And this also implies something else. If you do the exponential, so using exponential relation Fourier series, the orthogonality relation becomes integral e to the I mx e to the minus I nx dx. Okay. This is equal to delta mn. Okay. So, it has to be this is another 1 by 2 pi. Now, this is actually quite an interesting relation. Okay. Now, m and n are distinct. Okay. So, m can either be equal to or may not be equal to. Okay. This is so. So, this means that integral e to the I m minus n x dx from 0 to 2 pi, that should be equal to 0 if m is not equal to n. So, next what we want to do is to go from these Fourier series to something called Fourier integrals. Okay. And Fourier integrals are used for different class of problems. Okay. So, Fourier integrals is a more general version of this Fourier series, okay, where instead of having a discrete set of functions, okay, you have a continuous set of functions. So, that will be the next topic that we will do. So, we have seen the Fourier integrals, okay, and the Fourier integrals in the Fourier series, you represent a function as a0 by 2 plus sum over n equal to 1 to infinity a n cos n pi x by L plus b n okay. So this is a Fourier integral we have been discussing, and you should think about this in the following way. You should think about this as a0 by 2 plus, and if I write out the first few terms here, a1 cos pi x by L plus a2 cos 2 pi x by L plus a3 cos 3 3 pi x by L plus and so on, plus similarly for B1 for Bn. So, B1 cos pi x by L plus B2, oh sorry, this should be sine, should be B1 times sine pi x by L plus B2 times sine 2 pi x by L. Okay. So this is the Fourier series, and if we had this series, we said that an equal to 1 over L integral minus L to L f of x cos n pi x by L dx, and Bn is equal to 1 over L integral minus L to L f of x sine n pi x by L dx. Okay, so that is the description of An and Bn, and now what we said that the range of x, if f of x is periodic, then minus infinity less than x less than infinity. Okay. So, if f of x is a periodic function, this expansion can be done for all x. So, periodic I should specify periodic, this implies f of x plus 2L equal to f of x. So, periodic with period 2L. So, 2L is the period of f. Okay. So, let's put this separately. Okay. So, if f of x plus 2L is f of x, then this expansion is valid for minus infinity less than x less than infinity. So, whenever you have a periodic function, you can always expand it in a Fourier series. Okay. Now, there are a couple of things. One is we want to extend this to functions that are not periodic. So, that is what we are going to do in this next class, and when you do that, the natural extension becomes something called a Fourier integral. Okay. So, that is what we are going to do now. So, in the Fourier integral, I will try to motivate the Fourier integral in the following way. So, Fourier integral is valid for f of x not periodic. Okay. And so, how do you do the Fourier integral? And the way we will do it is we will motivate the Fourier integral by the following argument. So, imagine L tending to infinity. So, you just imagine that your length is tending to infinity. Okay. So, what was this L? L was the 2L was the periodicity of the function. Okay. So, our integral was from minus L to L. Okay. So, 1 over L integral minus L to L. Now, you imagine that L goes to infinity. So, this seems to go to minus infinity to plus infinity. Okay. Something else happens. If you look at all these, this is pi x by L, 2 pi x by L, 3 pi x by L, and so on. So, the various terms here, okay, they are of the form n pi x by L. Okay. So, if k n equal to n pi x by L, n pi by L. So, you denote n pi by L by k n. Okay. Then what happens is that so when as L infinity, the spacing between successive k values tends to 0. So in other words, if you look at kn plus 1 minus kn, okay, that's the difference between kn plus 1 and kn. This is just pi by L, okay, and as L tends to infinity, kn plus 1 minus kn tends to 0. Okay. So what happens is that in this sum, the successive k values become very closely spaced. Okay. So now you instead of writing this as a sum over n equal to 1 to infinity, I could write this as a sum over kn. So I can write write this as a sum over kn equal to pi by L to infinity. Okay. So this is identical to infinity. So that means it goes from pi over L, then in the next function it is 2 pi over L, 3 pi over L, and so on, all the way up to infinity. Okay. So I can write this in this form, and instead of a n, I denote by a k. I just called a k, instead of calling it a1, I will call it a k, a k n. Okay. So now what happens is that this f of x looks like a sum over a0 by 2 plus sum over kn equal to pi over L to infinity a kn cos knx plus b kn sin knx. Okay. So I wrote exactly this, but instead of denoting this coefficient as a n, I denote it as a k n. Okay. And the reason for that will become obvious. Now if you imagine that L tends to infinity, okay, then this sum, because the successive values of k are very closely spaced, this sum becomes an integral. So as infinity, sum over kn tends to integral over dk with some appropriate normalization factors. Okay, or actually more yes, tends to this quantity. Okay. So then what it will look like is let's ignore the complex term for now, but it will look like some integral. Okay. And I chose to do this in sines and cosines, but I could also do this with the exponential form. So this integral will be called the Fourier integral. So whatever the integral representation of this will be called the Fourier integral. Okay. And since L is tending to infinity, your range of integration will go from minus infinity to infinity, and you do not need to worry that the function is periodic, because anyway L is going to infinity, period is infinity. So it is as good as a non-periodic function. Okay. So let's so this is the motivation for using the Fourier integral and seeing how it works. Now let's take the specific example of the exponential expansion, and we will use that to represent the Fourier integrals. Okay. So the standard definition of the Fourier integral, in terms of, you can define it in terms of sines and cosines, but we choose to do it in terms of exponentials, okay, because that is the most commonly done Fourier integral. So in that, f of k is equal to 1 over root 2 pi integral minus infinity to plus infinity f of x e to the I k x dx. Okay. So f of k is written as f of x into e to the I k x it's okay. So it's written as e to the minus I k. Okay, so that your f of x, you can put a tilde on this. F of x is okay. So let's look at this. Okay, so you write f of x as an integral over dk f of f tilde of k. Okay, f tilde of k is like the coefficient of e to the I k x. So you should compare this with sum over n equal to 0 to infinity n equal to minus infinity to infinity c n e to the I k n x. Okay, so you should compare it with this. Okay, so in the exponential representation of the Fourier series, you had sum over n equal to minus infinity to infinity c n e to the I k n x. Now here instead of that you have since the k's are continuous, so the sum over n equal to minus infinity to plus infinity becomes integral over dk, okay, n e to the I k x. Okay, so this part is clear, and instead of c n you have f tilde of k. So f tilde of k should be thought of as the coefficient just like c n is a coefficient here. Okay, so there is a lot of similarity between this expression and that expression, and this is called the Fourier integral. Okay, there are some factors of 1 over root 2 pi put here, so that this f of x and f tilde of k have a very symmetric look to them. Okay. Now this is called the Fourier transform. This is called the inverse Fourier transform. Okay. Okay. Now when you look at this expression, you notice something, that what we have, suppose we started with a function of f of x. When we do the Fourier transform, you get a function of k. Okay, this is and I have used a tilde to say that this function is in general a different function. Okay, so you started with a function of x and you went to a function of k. Okay, so this is like a change of variables. So from x to k. Okay, and important thing is that both f x and f tilde of k, they contain the same information. So the same information that is in f of x is there in f tilde of k. So that means from f tilde of k I can calculate f of x, from f of x I can calculate f tilde of k. Okay, so it's like a change of variable, but not the typical change of variables that you do. This type of it's a change of variables x to k through something called an integral transform. Through an integral transform. Okay. So this f tilde of k is related to f of x through an integral. Okay. Alternatively, you can also think of this as, you can also, especially if you look at this connection. Okay, so this transform looks like a Fourier series. Okay, but instead of having discrete basis where n went through discrete numbers, you had a continuous basis. Okay, so this is, or you can think of this as a continuous basis function expansion. Okay, so either of these methods works. So you can think of it as an integral transform, a transformation of variables, or you can think of expanding the function in a continuous basis. Okay, so that is the other way. And notice that in this case you would say that your Cn is equal to sum over or will be integral f of x e to the minus I k n of x dx with some factors. Okay, let's not worry about the factors, but you had something like this. Okay, and in this case what you have is f tilde of k, which is what we associated with Cn. Okay, that looks like integral f of x e to the minus I k x. Okay, so there is a lot of similarity between this. So in a sense what you are doing here is just the same thing as this, but you are letting your case be continuous. Okay, so couple of more things I want to mention. One is that this Fourier transform will only define if f of x is piecewise continuous. So f of x has to be piecewise continuous. Okay, so it has to be a piecewise continuous, it has to be integrable. Okay, so these are certain conditions for the existence of the Fourier transform. So if your function is not piecewise continuous or integrable, then there is no then it does not have a Fourier transform. Okay, so now you come back to something in this case. In this case we said that the different basis functions were orthogonal. Okay, so we had relations like e to the I k n of x e to the minus I k m of x dx was equal to delta k n k m. Okay, so we had this orthogonality relation, okay, or equal to equal to 0 if k n not equal to k m. So we had this in the case of discrete. Now for Fourier transforms, the orthogonality relation takes a slightly different form. Okay, so in this case your k is a continuous variable, so then it takes this form e to the I k1 x e to the minus I k2 x dx. Okay, from minus infinity to plus infinity, and I will just put a 1 over 2 pi for now. One over root 2 pi. This is 0 if k1 is not equal to k2. Okay, so but since k1 and k2 are continuous variables, okay, this goes from a Kronecker delta function to something called a Dirac delta function. Okay, so this is called a Dirac delta function. Okay, so what is this Dirac delta function? I have to check whether this is 2 pi or root 2 pi. So what is I am not sure whether this should be 2 pi or root 2 pi. We will just come to that in a few minutes. Okay, so we will just leave this as this for now, but we will correct it if necessary. Okay, so what is a Dirac delta function? Definition of Dirac delta function, and some people are not comfortable calling it a function. Okay, but we will still use the same idea. So Dirac delta function, this so we will look at some characteristics. So delta of x equal to 0 if x is not equal to 0, delta of x tends to infinity as x tends to 0, and finally the most important part of the definition is that integral of g of x delta of x 0 d of x g of x delta of x dx, okay, this is equal to g 0. Okay. So this is a delta function, this is this is basically delta of x minus 0. Okay, that means this is equal to 0 if x is not equal to 0, okay, and it is infinity otherwise. Okay, and you can write this as the more general way to write it is delta of x minus a equal to 0 if x is not equal to a, delta of x minus a equal to infinity at x equal to a, and integral delta of x minus a f of x dx equal to f of a. So, this is the most important property of the delta function. You multiply a delta function by a function f of x, then you get the value of the function at a. Okay, so, f of x, so you multiply it by f of x and then you integrate over all x, you get the value of the function at a. Okay. So, this is the most important property of the delta function, and this is what is typically used as the definition of the delta function. So, this okay. Let us try to see what this delta function looks like. So, suppose this was my x variable and let us say this is a, this is my x variable. Now, f of x might have, and I show f of x, this is f of x. Okay. Now, this delta function delta of x minus a basically looks like it is 0 whenever x is not equal to a, and right at x equal to a it goes to infinity. So, it is very very narrow, it looks like this. Okay. And it is a very very narrow function, very very narrow, okay, and it goes to infinity. Okay. Now, now you can see when you multiply f of x by this function, okay, when you multiply these two functions, okay, the function that you will get will be 0 everywhere except in this region. Okay. So, this integrand, so this product is 0 everywhere except in the small region, okay, and in this small region your f of x is constant at f of a, okay, f of x is constant at f of a, okay. So, in this region, so I can write this as, I can say the following, dx is equal to f of a times integral delta x minus a dx, okay, and the only function that is non-zero is this small region, okay. So, and this delta function, so the area under the delta function is chosen to be 1, so equal to f of a, so this is equal to 1. Okay. So, the delta function can be thought of as this very very narrow function, okay, but it is very very tall such that the area under the function is 1. So, the integral of the delta function is 1. Okay. So, that is how you should think of the delta function, and delta functions are extremely useful in a lot of manipulations in this especially involving Fourier transforms. Okay. Now, We will discuss an application of delta functions when we talk about the position and momentum representations or the power spectrums. Okay. But what we want to do next is we want to look at some properties of these Fourier integrals. So, we look at some properties of Fourier integrals which makes them extremely useful in lot of engineering and science applications. Okay. So, we will use this definition of Fourier transforms, okay, and let us look at some properties. So, suppose g of x equal to d by dx of f of x. Okay, so, suppose g of x is d by dx of f of x, then what is g tilde of k? Is equal to 1 over root 2 pi integral minus infinity to plus infinity g of x e to the minus I k x dx. So, g tilde of k is this. So, the Fourier transform of g of x is this, and so this is equal to dx. Okay. And then what I will do is you integrate this by parts. So, if you integrate this by parts, you will get two terms. One is f of x e to the minus I k x at the boundaries, and this is 1 by root 2 pi. Minus integral f of x times d by dx of this, d by dx of that will give me minus I k e to the I k x dx. Okay. So, this term now f of x has to go to 0 at the boundaries, because only then the Fourier transform will be well defined. Also, we assume that e to the I k x goes to 0 at the boundaries. Okay. So, then this term is 0 minus two pi, and I will write it in a, I will take this minus I k outside. So, I will write plus I k times I k times dx. Okay. So, so this you notice this is just f tilde of k. Okay. So, what it means is that if g of x is d by dx of f of x, then g tilde of k is I k f tilde of k. So, so the Fourier transform of d by dx of f of x is I k f k f tilde k. Okay. So, this is the first property, and you can extend this. So, if it is second derivative, if h of x is equal to d square by dx square f of x, then this implies h tilde of k is equal to I k square f of k f tilde of k. Okay, and you can go on for all derivatives. So, each time you have a derivative you get a factor of I k. So, this is one useful property, okay, and this property is what will be used to. So, then what we will do is we will use the Fourier transform to convert differential equations into algebraic equations. Okay, so, instead of derivatives you just have multiplicative factors of I k. Okay. The next property that is very useful is the following. So, let us define the convolution of f and g. So, this is h of x equal to, it is denoted by f star g, and this f star g is a function of x. So, this is the convolution of f and g and it is a function of x. So, this is equal to integral dx prime f of x minus x prime g of x prime. Okay. So, it is just, so you take f of x minus x prime g of x prime such that they add up to give x, and you integrate this. Okay. You integrate this over the usual range, and this is called the convolution. So, now h tilde of k. Okay. So, if you calculate h tilde of k, you can show that this is nothing but square root of 2 pi f tilde of k g tilde of k. Okay, so, the Fourier transform of a convolution is nothing but the product of the Fourier transforms with some factor of 1 by root 2 pi. So, this is called the convolution theorem, and this is very useful when you want to invert Fourier transforms. So, when you have a Fourier transform of this kind and you want to calculate what is the function of which this is a Fourier transform, you can use this convolution theorem. Okay. So, what we will do next time is to use these theorems, use Fourier transforms to solve certain differential equations.